Hey there, welcome back to the channel. My name is Chris, and today I want to talk about performance monitoring. Specifically, we're going to be looking at interrupt performance. The first thing I want to measure is the frequency of the max interrupt handling that the platform can handle. So how fast can I give it interrupts and have it respond to those interrupts? The response will be very, very basic, very simple, but how fast can it do it before it really starts to fall down? The second thing I want to measure is when it gets an interrupt, how long does it take to actually react? So from physical action to physical action, timing all of the software goo that goes on in between those two things. So let's take a look at the hardware setup first, and then let's write some code. So we're going to need a few pieces of equipment in order to run this test. The first thing we need hardware. I've got here a Meadow F7Feather. This is a V2, but it is an STM32-based platform. Again, we could use some other hardware, Raspberry Pi, Arduino. In fact, if you're interested in seeing something like that, go ahead and leave a comment down below. But we then need some inputs for this. I could hook up a button, but I don't think I can push a button fast enough in order to test the limits of this. So we need something to generate signals. For that, we use a signal generator. Shocker. I'm not really well set up in this office to show a bunch of this stuff, so I've got cameras around me. My signal generator is over here to the side, but I will put it up over here as I video it from probably my phone. What the signal generator does is, as the name suggests, it generates a square wave signal. It can generate lots of different things, but we're going to just be using a square wave, 50% duty cycle. How fast can we run up and down with that wave and have the device handle it? The next thing we're going to need an oscilloscope. I have an oscilloscope here as well on the bench. I will put video of it over here. I do have a desktop application as well that we can look at for the oscilloscope. It looks like this. We'll also be taking a look at it from this perspective. The physical display on the scope gives a much better reading, so we'll take a look. We'll probably use both of them. So to hook up the hardware for this test, it's pretty simple. We've got leads that come from the signal generator, basically positive and negative. So this is generating the signal here, and this is the ground. We'll just connect the ground to the ground on the device, and we'll connect the signal to D05 here. No particular reason, it's just on the end, it's easy to find. Now let's go take a look at some code. So we're going to start out, we're going to need a stopwatch in order to time things. And we're going to use an interrupt port in order to receive these signals. D05 is what I have it hooked to. We're going to look at just the rising edge. We could do the falling edge. We could do both. Doesn't really matter. We just are picking an edge so that we can look at the frequency. I'm going to use an internal resistor to make things a little bit easier. And I'm going to turn off debounce and glitch. So I don't want the software having any filtering on the signal that comes in. Next, we want to look at this input port's signal, so when it changes, we want to count that. Now all we need to do is we need to record frequency. And frequency is just the number of cycles over time, so we're going to run a loop and count the number of these interrupts that we get in a given period of time. Since frequency really is cycles per second, if we measure this and do it once per second, the math becomes really easy for us. So really the frequency is just the count per unit of time. So we're going to capture the count, capture the time elapsed with the stopwatch, and then calculate the frequency. Then once we output that, we're going to reset that and restart the stopwatch. Then we'll sleep for a second, go back, do the capture, and output our frequency. So this should, in theory, give us in the console the same frequency that we see on the signal generator. All right, so let's reset the device and deploy the application. All right, so we've started up, and you can see the output says about 1 hertz, and that matches what we have on the signal generator. So let's up the signal just a little bit just to verify that our math is working. So that's 2, 3, 4, 5. So that appears to be working. So let's jump by a little bit more than 5. So now we're at 105, and that looks like it's pretty darn close to our math. Now let's jump by hundreds. So at 1,000, we're still right on. So let's jump by thousands. So here we're starting to see a breakdown. I've got it set for 6,000 and we're getting about 5980. So it's a little bit short. Let's try 7. You can see with 7, it actually goes downhill. So it is falling off. Basically, it's running into itself. It's getting a lot of contention and it's having to deal with that. So if we come back at 6, you can see we're running right around the edge. It's dropping out occasionally, and those are likely contentions that are happening inside the software. If I drop it down to 5, it's very, very stable. And if we want to try to get even closer, here's 59, 58. It looks like we've got a maximum of around 5.8 or 5.9 kilohertz on this. You might then wonder, is this a good or is this a bad number? There really isn't a good or bad answer for that. The application itself will dictate how fast it needs to be. If I have something that is ingesting a bunch of data based on an interrupt very fast at large frequency, maybe this wouldn't be adequate. But if I just am worried about a user pushing a button, they're not going to be pushing a button near this fast. So really it depends on what your application does, whether or not this is an appropriate level to meet your needs. You can use this, however, to look at this is what this platform is capable of at this given time. If I make changes to the platform, make changes to something, I can then look at it again at some point in the future and see if things have gotten better, if things have regressed, whatever. Could also use this to compare different platforms. If I do need, say, medium speed frequency handling, and I can look at this and I can go, well, this will do 5,900 hertz, and then I look at some other platform and it does better or worse, I can use that to make my decisions based on these numbers. The next metric I want to look at is kind of responsiveness of the system. Given some signal, how long does it take for the system to react and do something? Now, bear in mind that this is a managed code scenario. This is non-deterministic, right? We've got an operating system going on. We have a runtime that has a garbage collector going on. This is not going to be a hard number that we go, it is exactly this long to react. A real-time system can give you that, so something that has deterministic behavior. We do not have that in this case, but it still is useful to know how long the typical or the mean is, and as we do have those outliers, how big of outliers are those? Basically, that's called the jitter. How far does it move forward and back from that baseline? So let's go take a look at writing some code for this, how we're going to measure it, and then when we have the scope traces, we can talk about exactly what it means. So to start with, let's just modify the existing code. We don't really need a stopwatch here, and we still do need the input port, so that's going to have our input. But what we're going to do is when that input changes, we're going to set an output. So we want to create an output port, and we'll just put it right on the one next to it. Again, which one, it doesn't really matter. And when the output or the input interrupt comes in, we're just going to pulse the output one time. And that's all we're going to do. So for every input signal we get, we should get one pulse on the output. So let's go hook up the oscilloscope to that trace. We have the original probe connected to D05. We're just going to add a second probe to D06 so that we can see when the input signal happens and when the output signal occurs. We're not going to time this with code because I don't want the code for testing it affecting the results. Really what we're going to use is we're going to use the oscilloscope to measure this, this output. If I swap over to the scope view, I have the signal generator at a 200 hertz signal. The rate really doesn't matter. We could slow it down or speed it up. We basically want to take a look at just one of these edges. So a rising edge, and then the purple is the output, and it's going to come up for each one of those rises. So let's deploy the application first, and we'll take a look at what that looks like. Okay, so you can see that for each one of the rising edges on the input, which is the yellow, we have a rising edge on the output, which is the purple. So that's exactly what we're interested in seeing. So now let's zoom in on one of these rising edges and take a look at the time from when the rising edge happens to when the rising edge on the purple occurs. You can see on the screenshot here, let me move this a little bit. We've got the rising edge of the input here at a -301 and the rising edge of the output at a -101. So it looks like it's about 200 microseconds here. Another interesting thing here is this pulse, right? In our code, all we did was said high and low right here. So the amount of time it takes this platform to execute those two statements is this pulse here. So we are measuring the code execution time, and my guess is that looks like, I don't know, what, about 60 or 70 microseconds? Something like that. You can see, again, this is moving around, moving left and right, and sometimes it actually disappears. It probably is going off the right. Again, we've got the runtime going on here, though there probably isn't a whole lot going on in the runtime. It probably does have some background things that are going on, doing some checks. But we also have an operating system underneath that is running. So that provides some of that movement or jitter. Now I'm going to shut this off and we're going to move over to looking directly at the scope because it's a little bit clearer and a little easier to measure. You can see here, I have it set to persist. So that purple is giving a little bit of a faded background. What that allows us to do is to kind of visualize the jitter that's going on. I can also move the cursor around, and you can see it looks like it's about 206 microseconds from that rising edge of the input to the rising edge of the output. But you can also see that we've got things that are coming out quite a bit further to the right. You can see from the scope trace, 200 microseconds is pretty typical, with a vast majority of them in under 300. I'd have to do some data capture to get hard numbers for things like mean and median, but it looks like 200 microseconds is the typical, with almost all of them landing in under 300 microseconds. There are obviously some outliers because the system is doing something else, so we have occasional ones that fall outside of that, but most of them are in the 200 to 300 microsecond range. So again, this is a data point that allows us to look at the system and then know the demands of our application and go, is this good enough for what we're doing? For most applications, this would be more than adequate, but I'm sure there are applications that you could come up with that this is not fast enough. While I'm at it, let's measure the actual pulse width of that on-off of the output. Looks like about 75, 76 microseconds. There we go. We've now measured code performance and, in fact, platform performance using hardware, using an oscilloscope and a signal generator. Again, I did this on a Meadow F7, which is an STM32-based platform running a full operating system and a managed code environment. If you're interested in this, I could also run this on, say, a Raspberry Pi, maybe a Pi Zero, and even run a similar test on an Arduino, obviously not with the same code, but to get some other feel for what some of these other platforms can do. If that's of interest to you, go ahead and leave a comment down below. Otherwise, that's all I've got for you for today. Thanks for watching.